In the peasant episode, the whole algorithm rested on a single structure, a monoid. One associative operation and an identity element. Give the power function any monoid, and it computes powers by repeated squaring. The accumulator post reused the very same structure for streaming statistics.
But what happens when you have two operations instead of one?
The answer is a semiring. A semiring is two monoids living on the same set, linked by a compatibility condition. We write it as a 5-tuple. The set S, an addition, a multiplication, and the two identity elements, 0 and 1. The plus and the times each form a monoid on their own. What turns a pair of monoids into a semiring is how they fit together. 4 axioms pin it down. First, the set with plus and 0 is a commutative monoid. Addition is associative, has identity 0, and the order does not matter. Second, the set with times and 1 is a monoid. Multiplication is associative with identity 1. Third, multiplication distributes. Over addition. Take the symbol A and multiply it by the sum of B and C. That comes out the same as A times B plus A times C. And fourth, 0 annihilates. 0 times anything is 0. These are the rules ordinary arithmetic obeys, stated abstractly enough that other structures can obey them too. In C++20, we capture this with a concept, using the same free functions 0 and 1 from the peasant post. A type is a semiring if you can add two values, multiply two values, and ask for its 0 and its 1.
But does the compiler check that the axioms actually hold?
It checks syntax, that the operations exist and return the right type. The axioms, associativity, distributivity, annihilation, are semantic promises the programmer must keep. The compiler enforces the shape, you enforce the laws.
Wait, the integers I already know with plus and times, that is a semiring.
Exactly the ordinary addition and multiplication you have used since childhood. But they are only one example. There are others, and here is the surprise that drives this whole episode. Each one corresponds to a different graph problem. 5 semirings, 5 questions about a graph. The Boolean semiring. Where plus is or, times is and 0 is false and 1 is true, answers reachability. Is there a path? The tropical min semiring. Where plus is min and times is ordinary addition, with 0 infinity and 1 0, gives shortest paths. The tropical max semiring. Where plus is max and times is addition, gives longest paths. The bottleneck semiring. Where plus is max and times is min, gives widest paths. And the counting semiring. Plain addition and multiplication counts the number of paths.
Hold on, plus is actually min, that sounds backward.
The naming of the tropical semirings is counterintuitive, but it is standard and it matters. In the tropical min semiring, the addition of the semiring is min, and the multiplication is ordinary addition. Read that again. The thing we call plus is actually min, and the thing we call times is actually plus. This is not a quirk. Matrix multiplication uses both operations, and the algebra has to line up so that the inner product of a row and a column computes the best path through an intermediate node. The shape is what makes it work. Each semiring is a small struct, an operator plus, an operator times, and the two free functions 0 and 1. Here is the Boolean one. Plus returns val or the right-hand side. Times returns val and the right-hand side. 0 is false, 1 is true. A dozen lines, and reachability falls out for free once we put it in a matrix.
Wait, if a semiring can measure a single edge, can it measure a whole path through matrices?
Now the key move. Matrix multiplication needs exactly two things, a way to multiply entries and a way to add the products up. That is precisely what a semiring provides. So if S is a semiring, then the n by n matrices over S form a semiring too, with entry-wise addition and the usual row times column product, using S's own operations. The construction is closed. Matrices over A semiring are again a semiring. This is the accumulator posts lesson at a higher level. There we composed monoids with a product construction. Here we compose two monoids through distributivity, and the result composes again into matrices. Represent a graph as an adjacency matrix over A Semiring. The entry at row I, column J holds the weight of the edge from node I to node J, or the Semiring's 0 if there is no edge. For shortest paths, that 0 is infinity. For counting, it is the integer 0. For reachability, it is false. One matrix, and the Semiring decides what an absent edge means.
So the same formula means something different every time.
Here is the heart of it. Compute A multiplied by itself, k times. The entry at row I, column J combines, over every k hop path from I to J, the product of the edge weights along that path, and then takes the sum across all such paths. What product and sum mean depends on the Semiring. In Boolean, product is and all edges must exist, and sum is or any path will do. In tropical min, product is addition, a path's length is the sum of its edges, and sum is min, we keep the shortest. In counting, product multiplies the choices along a path, and sum adds up the paths through different intermediaries. One inner product of a row and a column, 5 different meanings. To answer for paths of any length, we add up the powers. The identity plus a squared on up to a to the n-1, where n is the number of nodes. With no negative cycles, n-1 hops cover every simple path. We call this the closure. And the individual powers use the very same repeated squaring algorithm from the peasant episode. The power function does not know whether it is computing reachability, shortest paths, or path counts. It only knows it has a Semiring. Let us make it concrete with a 4-node graph. Node 0 points to node 1 with weight 2, and to node 2 with weight 5. Node 1 points to node 3 with weight 3, and to node 2 with weight 1. Node 2 points to node 3 with weight 4. We build the adjacency matrix once from this single list of edges. Now the call we will pin in place, closure of A itself. The graph stays fixed. The only thing we will change is the Semiring. Start with the tropical min Semiring, shortest paths. Ask for the distance from node 0 to node 3. There are 3 routes. 0 to 1 to 3 costs 2 plus 3, which is 5. 0 to 2 to 3 costs 5 plus 4, which is 9. 0 to 1 to 2 to 3 costs 2 plus 1 plus 4, which is 7. The Semiring's plus is min, so it keeps the smallest, 5 along 0, 1, 3.
Wait, what about the direct edge from 0 to 2? Is 5 really the best it can do?
Notice 0 to 2. The direct edge costs 5, but going through node 1 costs 2 plus 1, just 3. The closure finds it, 3 not 5. Keep the call, keep the graph, swap the Semiring to counting. Where plus is ordinary addition, and times is ordinary multiplication. Now the entry from 0 to 3 is no longer a distance, it is a tally. How many paths run from 0 to 3? 3 of them, 0 to 1 to 3, 0 to 2 to 3, and 0 to 1 to 2 to 3. The answer is 3. Same matrix power, a completely different question.
Can we ask something sharper, like how many paths use exactly so many edges?
That is just the bare power, a to the k without summing. A squared gives the 2 paths of exactly 2 edges, 0 to 1 to 3, and 0 to 2 to 3. A cubed gives the 1 path of exactly 3 edges, 0 to 1 to 2 to 3. Add them, 2 plus 1, and you recover the closure's answer of 3. The closure is just the powers summed. Swap again to the tropical max Semiring, where plus is max. Now we get longest paths. From 0 to 3, the longest of those same 3 routes is 0 to 2 to 3, at 5 plus 4, which is 9. And swap once more to the bottleneck Semiring. Where plus is max and times is min, a path's capacity is its narrowest edge, and we want the widest such capacity. From 0 to 3, the route through node 2 has bottleneck the min of 5 and 4, which is 4, and that is the widest. The answer is 4. And the simplest question of all, swap to the Boolean Semiring. Where plus is or and times is and. Now we are asking only, Is node 3 reachable from node 0? Yes. In fact, node 0 reaches every other node.
Wait, node 3 does not reach anywhere itself.
Node 3, by contrast, is a sink. It has no outgoing edges, so it reaches nothing but itself. The same closure that gave us distances and counts now gives a single bit of truth. One graph, one call to closure. 5 semirings and 5 different answers to how node 0 relates to node 3. Reachable, shortest distance 5, longest distance 9, widest capacity 4, and 3 paths in all. The topology never moved. The Semiring chose the question.
So this is the same lesson as the peasant episode, just one level up.
Step back and see the pattern. The peasant episode established it. Identify the algebraic structure, then write the algorithm once. There the structure was a monoid, and the algorithm was power. Here the structure is a semiring, and the algorithm is still power, now applied to matrices. We did not write a shortest path algorithm, a longest path algorithm, a reachability algorithm, and a path counter. We wrote one matrix power and chose different semirings. And the structures themselves compose. The accumulator post combined monoids with a product construction. This episode combined 2 monoids through distributivity to form a semiring, and then combined those into matrices, which form a semiring again. Same principle at a higher level of abstraction each time. Structure stacks. This is Stepanov's thesis, made vivid. Algorithms arise from algebraic structure. The more structure you identify, the more algorithms you get from the same code. We did not write 6 clever graph algorithms. We wrote one matrix power and found 6 questions a graph can answer. Is there a path, the shortest, the longest, the widest, how many paths in all, and how many of exactly k edges?
The topology never moved, only the question changed.
The structure chose the question. See the structure first, and the algorithms follow.